All right, so like I said, the first half of the class is basically continuum mechanics or theoretical polar elasticity. And so really when we're talking about continuum mechanics, we're going to start, ultimately we're talking about a conservation of mass, momentum, and energy, okay? But in order to specifically describe conservation of momentum, we need to talk about kinematics for a second, right? So kinematics is basically the geometric description of motion, okay? And so, if you remember from your undergraduate solid mechanics class, you learned about stress and strain, right? And so really that's what we're going to look at, three-dimensional descriptions of strain that when then paired with some constitutive model can give us stress, okay? And then stress, we use stress sort of in a graduate school version of F equals ma to solve for the displacements of a body, okay? Given the strain that we can, in a constitutive model, we have stress, which, stress is like a normalized force, and then we can use that in a graduate, conservation of momentum equation, and we solve it, okay? So that's sort of where we're going with this, and we're going to start with strain, okay? So strain is very crystal clear when you're an undergraduate student, right? It's like the change in length over length, right? And the reason we want strain as opposed to, or the reason we prefer strain as opposed to some other measure of deformation, because that's really what we're trying to do, describe deformation, right? The reason we like strain is because it's a normalized measure, right? And the reason we want a normalized measure is we want to be able to compare the strength of different materials, right? So imagine we have a piece of steel, right? Steel is fairly homogeneous material, right? I mean, yeah, it has defects and grain boundaries and other things at a very, very small scale, but on the scale of most structures we build with it, right? The defects and the heterogeneity are small. So in other words, think about an automobile or a bridge, a steel member in a bridge. The grain size is tiny compared, it's orders of magnitude smaller than the scale of the steel member in the bridge, and therefore we just, for most practical purposes, say it's a homogeneous material, okay? However, contrast that with a material like concrete that is fairly heterogeneous, even at the scale that we build things out of it, right? I mean, think about a concrete member in a bridge. If you walk up close enough to it, you can see aggregate, right, with your bare eyes. You can't see grain boundaries in a steel with your bare eyes, but you can. So the thing is, when we go to the lab and do experiments on different materials, we need to have a large enough sample such that we can say that the deformations are homogeneous, right? And that any kind of heterogeneous defects or other things are small compared to the sample size, okay? So that means when we go to the lab and we do material testing to determine the strength of steel, we can get away with fairly small samples, right? But when we go to the lab and do tests on the material strength of concrete, we have to use fairly large samples, right? And we want a way to compare the strength of those two materials, and so we have to normalize it in some way, okay? And this is so when we talk about strain, we talk about, it's a normalized deformation, okay? So from your undergraduate class, you probably remember if you have a bar that has original length L0, and say you pull on that bar and you stretch the bar by some delta L so that its final length is LF, the final length, right? Then we define strain in undergraduate as sort of this, what we call the engineering strain, or certainly what an experimentalist would call the engineering strain, is the change in length over the original length, or the final length minus the initial length over the initial length, right? And if we take the final length over the initial length and we call it lambda, may give it a name like maybe you call it stretch ratio, then then this measure of strain is lambda minus 1, okay? And so this is the engineering strain. Now, the choice to normalize it by the original length was arbitrary, right? I made that choice. I said I want to divide by the original length to get a unitless measure. But what else could I normalize by? The final length, right? That's an equally valid choice. I could also normalize by the instantaneous length, right? In other words, as I'm doing an experiment, I could normalize by the length at the length of the sample at every data point I'm collecting along the way, right? The instantaneous length, right? I could also normalize with some other length. I could normalize it with respect to the length of that wall, right? It's really arbitrary, okay? And so just to sort of summarize, we call this the engineering strain. Certainly if you're an experimentalist, you call this the engineering strain. Sometimes you'll heard this referred to as the Lagrangian strain. And that's because later on we'll talk about Lagrangian or Eulerian coordinates and Lagrangian or Eulerian formulations of the field equations. And Lagrangian sort of always means with reference to the original undeformed configuration, right? And that's what we have here, right? LO was the original undeformed length, and we're referencing or normalizing by that. Therefore, we call this the Lagrangian strain, okay? But as we already talked about, there's other strains, like for instance, something called the logarithmic strain. Called the logarithmic strain. And this is the strain that you get if you normalize by the instantaneous length L, right? So this is the instantaneous length that we're dividing by, and DL, or the change in length, is now a differential because it's, at every DL or every increment of deformation, we're going to normalize by the instantaneous length. And so if you then, compute this integral, what you get is the natural log LF minus L0. And of course, we labeled this LF over L0 as lambda, right? So it's also the natural log of lambda. And this is known as logarithmic strain, or the natural strain. And sometimes, particularly in experimental papers, you'll see this called the true strain. Right? I don't like true strain because there's in more theoretical papers there's another measure of true strain, and they aren't really one-to-one. So, I prefer to see this called the logarithmic strain or the natural strain. And you'll see right away that, what I said, the normalization is arbitrary. And the reason it's arbitrary is because they're related, right? Look at this equation up here, right? If I solve this equation for stretch ratio, then I get that the stretch ratio is equal to the engineering strain plus 1, right? So then I can plug that in here, and I can get that the logarithmic strain is the natural log of the engineering strain plus 1. Right? And this is often what we do in the lab. If we report logarithmic or true or natural strain, we're not measuring it, or we typically don't actually do that. We just compute the engineering strain. It's very straightforward. We just divide by the original length, right? And then we take the natural log of that engineering strain plus 1, and we get the true strain, or the logarithmic or natural strain. Okay, so there's another measure that you might call true strain, and that is the final length minus the original length over the final length And in terms of the stretch ratio, it's this equation. And we call this guy the Eulerian strain. Or sometimes it's also known as the true strain. So because of this sort of conflicting definition, I just prefer to not use that term. Just call it the Eulerian strain. And again, it makes sense because just like Lagrangian was with respect to the original or undeformed configuration, Eulerian then is with respect to the final deformed configuration. And so since they're all related, you can probably see that you could also, there's something called the Seth-Hill strain measure. And it's, at least for this family of strains, it's sort of a way to write them all compactly in that you have a parameter m, so the strain is then 1 over m, lambda to the m minus 1. And you can just see by inspection that if m is 1, you get the engineering strain. If m is minus 1, you get the Eulerian strain. And if m is 0, you get the logarithmic strain.